All right, in this video, I want to expand on the idea from that last video that much of what we perceive is a layer of interpretation added by our brain rather than straightforwardly seeing things exactly how they hit our eyes. So let's start with an example of your brain using cues and context to interpret the proximal stimulus it receives. Probably one of the most famous perceptual effects is something called size constancy. When the same object is far away, it takes up less of our visual field, like just a tiny bit of angle, but we still perceive that thing as the same sized object. We just perceive it as a normal object far away, right? We don't perceive it as literally shrinking, even though less and less of it is hitting our eyes. Like in this example here, there's a man in a white shirt there off in the distance hiking down a trail. So that looks like a normal sized man. It just looks like he's far away, right? But if I take that same thing from the image, that same proximal stimulus, I just copy paste it. So I use Photoshop to put that exact same bit of the picture to a different place in the picture, which the depth cues tell me is closer to me, then the only way that white shirted dude would be taking up so little of my visual field, that same little angle of my visual field, while being so close to me, the only way that would work is if he's super tiny, a little knee-high hiker guy, and that's what we perceive in the rightmost picture, right? The little guy down here. But that's because our brain, taking the exact same input, will have two different things that we perceive from it based on other assumptions, other information in the picture. So day to day in normal life, when my friend is walking, or let's say my friend is far away from me and walking up closer to me, the visual angle that she takes up gets bigger and bigger and bigger. Like you can literally see more of the light bouncing off of her will hit larger swaths of my retina. That's what I mean by a bigger angle of the visual field. That either means, as that gets taking up more and more of my visual field, that either her body is the same size and she's just getting closer to me, or it means she's staying at the same distance way out there, but just growing taller and taller and taller and taller. Both of those would cause the same input to my eyes. But our brain has to disambiguate and guess which of those it thinks is more likely. And based on our past experience wandering around a world, right, a three-dimensional world, based on our knowledge, our brain guesses that objects like people don't usually change size, so it makes us perceive the friend as getting closer. That's a good thing, right? Another way to think of this is that our eye would get the same like circular input from a small circle that was near us, or a medium-sized circle a little further away, or a larger circle that was much further away, or literally any of an infinite variety of other possibilities, as long as they take up that same angle, right? So all those would take up the same visual angle, making the same light input on our eyes, the same proximal stimulus activating our retina in the same way. Which means in all those situations, the brain gets the exact same bottom-up information about the circle itself. A tiny circle and a huge circle hit the eye in exactly the same way if they're at different distances. So the neural signal to the brain, the pew, 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 pew that the brain gets, that's all the brain ever gets, right? The brain can't see. The brain just gets pew, pew, pews from our sensory detectors. That neural signal to the brain is super ambiguous. The brain actually has a really hard task here. It has to infer or make an educated guess which of those infinite possibilities it happens to be looking at. It has to guess at reality when the input alone can't tell us. So what does it do? It uses hints, like other information in the visual field, that tell us something is close or something is far. So size constancy is why this looks like a big-ass monster chasing a smaller monster down a tunnel. The lines in this image make us perceive the tunnel as a three-dimensional space. So the upper right monster must be farther away. And the only way it could take up the exact same amount of visual field as the lower left monster is if it's far away and huge, right? Because if you measure these, they're actually the exact same size. You can put your finger up against the screen or whatever. They're the exact same size. So size constancy, it's a very normal process and a helpful process that's usually right. But since it's just making a guess with the context info it has available, we can end up with visual illusions like this one on the right, where the shoe looks big enough to smash those people, right? That's because we don't have anything in the picture to tell us at what distance or depth that shoe is. So our brain can't quite as clearly disambiguate between like a normal sized shoe that's close up or a giant shoe that's far away. And in this case, we do have some top-down knowledge from our past experience that shoes don't actually get that big, right? But There's also some cues within the photo itself because the people are being silly. Those poses by the little people acting like they're about to be smashed, that's an additional cue the brain uses, so that weighs it toward maybe being a giant shoe in the distance. And we have trouble, we can kind of flip back and forth. We might perceive it both ways, right? If you look at it for a few seconds, the brain might allow you to see it either way, but not both ways at the same time. Your brain is just trying to figure it out, but it's coming up with some guess of reality, and that's what we perceive at any given time. By the way, size constancy also explains what's called the Ponzo illusion. Like the top yellow line here, when I don't have the little red thing showing the answer, the top yellow line here, it looks a little longer for most people than the bottom one. And that's until we actually, verify by comparing them with these red lines, you can see they're actually the same length. But the top one is perceived as longer. We usually see it as and experience it as longer since it's the only way that it would take up that much of our visual field if it was further off in the distance like that. So it just feels longer, even though the proximal stimulus of light hitting your retina gives the exact same visual angle for both of these lines. Our perception doesn't always match reality, but that's good because we want to be able to perceive things off in a distance, right? This is another fun example of that Ponzo illusion. Might even be more clear for you. If you just glance at this picture or look around to the sides of this picture and look back, like one of these critters looks much bigger than the other, right? The one further back, if this had depth, right? But if you hold your finger up to the screen, you'll see both of these critters take up the exact same amount of your screen. They're hitting your eye in the exact same way, and yet our brain has to interpret, and since it's kind of assuming the one at the top of the image is further back in depth, is further away from me, the only way it would be the same angle as this close-up little guy is if that one far away from me is gigantic. And now we understand why. So the brain, it's making an assumption. Context and hints in the rest of the picture, that's what tells us the top critter is far away, that we're looking at a 3D world with depth. So it infers that the top critter is huge, and that's why you see the top critter is bigger, even though that's not what hits your eye. Same thing here. All three copies of the car here are physically the same size on the screen. Again, you can hold your finger up to the screen and see that all three of these cars are the same size. But when you just look at this picture, it's almost impossible not to perceive them different, right? And that's due to the automatic size constancy process that our brain does behind the scenes all the time. Makes the left car look way bigger than the one on the right. This is actually easy to test in the laboratory. Like in a classic study from the 1940s, they put circles at various distances down a hallway, but the circle was always taking up 1 degree of the visual field. So big circle was just far enough away to be at the same angle as a small circle closer up. Then the participant, when they're looking at these different circles at different distances, but same angle, the participant would adjust a comparison circle just to kind of share how they were perceiving the size of what they saw down the hallway. Now, since every circle hits the eye the same way here, the question is what guess the brain would give, like what perceptual experience it would construct or invent from this. Now, in condition 1 of the experiment, they set it up to provide some depth cues to the eye. So the way they set up the hallway, it had depth cues so people could see kind of how far away something might have been, in which case the participant's judgment of the size was accurate. But in condition 2, they set things up in the hallway so that it provided no depth information. And at that point, judgments of the size of the circle were based simply on the size of the retinal image. And actually, researchers have used this principle, like size constancy, to create some really fun tricks. Like there's one called the Ames room. In the picture here, the woman on the right, she looks huge, right? But in reality, the women here are of similar height. The reason we perceive it inaccurately, and it seems or feels or we perceive it like one of these women is bigger than the other, is because the room's been constructed in a really unusual way to take advantage of the way the brain normally works, to trick the brain into perceiving the women at as if they're roughly the same distance, even though one of them in reality is significantly further away than the other. So this only works because our brain is used to tiles on the floor being the same size and shape, not changing a little bit in size and shape systematically in ways that trick us, right? Likewise, we're used to walls being at right angles, not weird-ass angles that are systematically manipulated like this. But that's the whole point. Our brain is making assumptions about things, in this case, usually reasonable assumptions, about things based on what it's learned is most likely from our past experience. It's taking advantage of what we might call environmental regularities, the way the environment normally works for us. Here's a short video actually explaining how the Ames room is designed.
Does what we see correspond to what's really out there? Or does our brain construct its own version of reality, one that does not always match up with the physical universe? Check me out, for example. I am the same size here as I am over here, but over here I look much larger. No, it's not a cheap video trick, it's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight, so the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you probably guessed, this isn't the case, and the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal the room's true shape. And of course, we easily believe in a box shape because that's the shape rooms normally are. This clever setup is called the Ames illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific American's Instant Egghead, I'm Ingrid Wickelgren.
So yeah, when we set things up in a tricky way, we get illusions. But the process of size constancy, it's normally a good thing, and it's usually correct when we're not messing with it on purpose. By the way, you might have noticed that the moon generally appears larger when it's on the horizon than when it's higher up in the sky, or maybe someone's pointed that out to you before. This is how most people see it. It's called the moon illusion, because obviously the moon doesn't actually change size, but in fact, it's not changing distance either. So it's the same visual angle, whether it's right at the horizon or way up in the top of the sky. But when it's on the horizon, we've got all those other depth cues that trick the brain into thinking it's further away, in which case it must be huge to still take up that same visual angle, which you'd then think the moon up in the sky would seem even further away, right? And taking up the same angle, so it should seem absolutely gigantic. But it turns out that's not how people normally perceive the sky, as being kind of as far away as you would think. So in fact, studies have shown that when you ask people to pretend and to think of the sky as sort of a surface around them, and then you ask them to compare the distance to the horizon and the distance to the top of the sky, so to speak, on a clear moonless night, they usually say the horizon appears further away than the sky up there. So under that mistaken assumption, right, that's not really how space works, but under that mistaken perception of the horizon being further off, then when this moon of the same visual angle is over there, it has to be bigger to create that visual angle while being presumably further away. So it's an illusion, right? The moon isn't further away or different sized at all, but our brain jumps to conclusions, and in some cases does so in way beyond our conscious understanding and knowledge of how the sky and space works. It kind of overrides on our knowledge of how the moon actually works, and we have this mistaken perception of the moon being larger when it's near the horizon. Try and take note of this. If you ever watch the moon rise and then watch it when it's in the sky, you'll notice the same thing. All right, but let's move on from size constancy and talk about another example of your brain using cues and context to interpret the proximal stimulus that hits our retina. So here, I've drawn some simple figures in PowerPoint. We have names for these different shapes, right? Like a rectangle for the left one, The next one might be an isosceles trapezoid. Third might be a diamond or a rhombus, and maybe a different trapezoid after that. All of these are clearly distinct shapes, right? And that would be obvious if you took out a protractor and measured the angles. Except, what if I told you that all these are the same object, just viewed from different angles? Like, think about the outline of the door in each of these pictures. On the left, the door's outline is a rectangle. But as we go further right, the door's image hitting our retina shifts to different trapezoidal shapes. So as we go about our day-to-day life in a three-dimensional world, the same object will actually make different shapes on the retina depending on the angle we view it from. But we don't perceive the door as changing shape. Like, oh my God, the door is getting taller on one side. No, we perceive it as the same object, but perhaps one side getting closer to us or further at a different angle. So our ability to perceive things that way, it's called shape constancy. Kind of like size constancy, but now it's shape constancy, meaning the door still seems and feels like and is perceived as being the same constant shape, even though it's making very different shapes on our eyes. The proximal stimulus changes, but our brain doesn't perceive it as the object changing. And this stuff may seem silly and obvious to you, but it's actually an incredibly tough problem for the brain to solve. That's because the proximal stimulus hitting our retina, like in this picture here, where a rectangular pattern of light is what hits the eye, that could come from a literally infinite variety of possible realities out there. And the brain will get the same input in all cases, leaving it to just guess. And when we've got other hints, like shadows or one object occluding another, we can then deduce distance, right? We can deduce the distance somewhere. But without those cues, our brain is stuck guessing based simply on how it has learned that the world tends to work. So if what we're seeing as elements of notebook paper, we've learned from past experience that notebook paper tends to be rectangular, so that's the best guess. And if it looks more like notebook paper than a poster, we assume it's roughly the size of an 8.5 by 11 rectangle close to us rather than a 59 by 77 inch rectangle further away. In all these cases, though, that's the brain using environmental regularities, basically unconscious probabilistic reasoning based on data from all of our past experience in the world. Without that, we'd be just as likely to perceive the middle of these three possibilities or one of the infinite other theoretical objects and distances that would make this exact same impression on our retina. And indeed, people raised in a different environment, like those born and raised in a jungle without a bunch of buildings that have right angles, they tend to not experience some of the same visual illusions we do. Different environmental regularities, different brain experience throughout your lifetime, different assumptions your brain jumps to when shown the same proximal stimulus. But now let's move on to one last version of constancy, one last example of how your brain uses cues and context to interpret the proximal stimulus rather than just perceiving exactly what hits our eyes. So if you glance at this image or just kind of follow the swirls around with your eyes, it's clearly got some blue spirals and some green spirals, right? Except that's not technically true. The parts that you see as green and the parts that you see as blue, those are the exact same color. And you might be like, what? I don't believe you. But let's zoom in a little bit. If I zoom in, try to ignore the orange and purple lines here. And you'll see that the bits surrounded by orange or the bits surrounded by purple, in other words, what we saw before as blue and green, they're actually the same color. But our brain perceived it as a different color based on the comparison with surrounding colors. We don't perceive color purely based on what wavelength of light hits our eyes. We perceive what our brain guesses the underlying color of the object is based on deduction from the wavelength of the light plus other lighting information we have, other contextual factors. Here's actually the exact same illusion, just presented differently. The green and blue stripes here are the same color, but it's hard not to perceive them as different. When you just glance at this, if you step back, walk to the other side of the room, look back here, you're going to see green and blue. You're going to see two different colors, even though it's the exact same thing. What's going on here is a process called color constancy. We perceive objects as the same color even when the lighting conditions mean that the proximal stimulus reaching our eyes is not the same wavelength of light. What do I mean by that? Well, think about how things look when you're out late at night or when you're in a dim room with very little lighting. Like, here's an example. What color is the banana here? Most people look at this and they're like, the banana's yellow, the grapes on the left, what are they? They're green, obviously. What about the blueberries near them? Most people say, yeah, definitely got to be a bluish or purplish hue, right? That's what we see when we look at this. We see the banana as yellow. But now pay attention to how different the actual stimulus is. What hits our eyes is very different when seen under different lighting conditions. So it's the same object, right? It's a banana. It's just a thing out there in the world with a certain molecular structure. Some wavelengths of light bounce off it and some don't. Under daytime lighting, we would all call it yellow. But even in the dark, when it's dim lighting, when we look at a banana, we see it as yellow. We perceive it as yellow, even though we're seeing very different things, very different proximal stimulus hitting our eyes under different lighting conditions, like kind of the left half and the right half of this square here. So what color is the banana? What's reaching our eyes? It's very different in these two conditions, but our brain works hard to make our perception in either case see the object not as changing color or as a weird blue-gray banana, but as an object with constant color that happens to be in shade right now or happens to be well lit or whatever. So the banana gets perceived as yellow, even though the light hitting our eyes from the banana is made up of entirely different wavelengths. Indeed, color constancy is the formal name for the effect we saw earlier with the viral video about the dress, right? So here's just another example of that same thing. Again, the brain's taking into account lighting information, brightness information of the surrounding scene, and it's correcting for it. Basically, this is a sort of subtractive method. It's subtracting out the effect of the environment's lighting, and that's what the brain makes us perceive. So same thing here on the bottom. We got a little square of paper that does not change in any way. The light bouncing off that little square and hitting our eye is always the same. But when the brain sees it as within a dark, poorly lit environment, it must be super freaking white to still hit our eyes the way it does. Whereas when the brain sees it as within a bright, well-lit environment, like on the right here, it must be super freaking dark to still hit our eyes the same way it does. So same input to our sensory system, same input to the brain, but what we see, what we perceive is an invention. It's a calculation. It's a best guess that the brain did, prior to us ever having the conscious experience of seeing the object. So now let's look at this checkerboard here. It's made up of a bunch of alternating light and dark squares, right? Dark square, light square, dark square, light square, predictable pattern. So let's start with an easy question as a warm-up, like which is the darker surface between square A and square B? If your answer was that A is the darker square, that is a perfectly normal and reasonable answer because it's what your brain invented. It's what all our brains invent by using color constancy. But actually, both of these surfaces are the exact same color, the exact same brightness. The A and the B surface area, no difference between them. You can check this in Photoshop where it'll just show the exact same RGB value on both surfaces, or just cover up the rest of the picture with your hands and you'll see that A and B surfaces are the same. But we perceive B as lighter because other cues tell us it's in a shadow, which means for the same wavelength to be hitting our eye as what's hitting our eye from square A, if B's in a shadow, it must be a brighter color, right? So we perceive B as being brighter than A, even though they're actually the same in this case. Or here's a fun one. I've just put a yellow lighting or a blue lighting over the same cube. So I might ask, how many squares are there on each face of the cube? And you could count it out, right? Or just notice it's 5 by 5. So there's 25 squares on each face of the cube. Pretty easy, right? And let's look at, say, the top of the cube. How many blue squares are there on the top of the cube? So go ahead and count it out. How many blue squares are there on the top of the cube? Count them out. 1, 2, 3, 4. I got 4. And that's probably how many you counted too, right? But what if I told you 7 is an equally good answer here for blue squares on the top? You'd be like, that doesn't make sense, right? We don't see that. We don't perceive that. But the blue squares on the left, so in the left image, the one you see is the blue squares. There's 4 of them, including the one the lower left on that top face. That color is the same. The thing hitting your eye is the same from those 4 squares as the 7 yellow squares on the right one, right on the top face on the rightmost cube. So this and this and this and this and this and this and this, those are the same color hitting your eye as this, and this. What you saw is the blue squares. Also, by the way, just for a total mindfuck, the middle squares on each face, the brown and the orange, they're the exact same color. Like this middle square and this middle square, exact same color hitting your eyes, or this middle square and this middle square, exact same color hitting your eyes. So what we call brown or orange, what you see, what you perceive that way, that doesn't actually mean different colors hitting your eyes. They show up as identical if you sample each one in Photoshop or if you just cut and paste this image and put them next to each other. what is projected from the screen, from the distal object on the screen, what's hitting our eyes, giving us the proximal stimulus, that is the same for the blue squares on the left and the yellow squares on the right, as you can see by just sampling them out. They've pulled it out to the bottom here, right? But based on context, in other words, based on lighting assumptions, what our brain knows about the rest of the lighting based on the background, the brain makes us perceive that same exact light input as being blue or as being yellow. And that's because it's subtracting away the background lighting conditions. So here up top, we've pulled out the actual colors in each of the picture. The tiles that you saw as blue in the left picture, they're actually a grayish color that's hitting your eye. The tiles you saw as yellow, they're indeed yellow, but the tiles you saw as red up top there, you can see it's an orange hitting our eye actually. And for the one on the right, for the cube on the right, the blue tiles, they're indeed blue, but the tiles you see as yellow, those are that grayish color again hitting our eye. And same one that made up the blue on the left here. So the exact same blue and yellow there. The tiles you perceive as red on the right cube, those are more of a purple in terms of what the rods and cones in your retina are getting. If you don't believe me, I can actually just clip out a tiny little bit of the picture without all the context. So look closely at the top right of the cube in the back row here. Look at the back of the right side cube. And look when I just take that little sample out. So where that red meets that yellow, just watch it. It's red and yellow, right? Exact same thing, but I've just cropped out that little bit of the picture. It's from the exact same picture. I just cropped it out. But there it looks gray and purple, right? Here, the exact same color hitting your eye from the exact same part of the image, red and yellow, purple and gray, red and yellow, purple and gray. When our brain isn't getting lighting information and subtracting all that out, then all it has to go on is the actual wavelength coming off the screen and hitting our eyes, a gray and a purple. But we perceive that same stuff differently thanks to color constancy, subtracting out background lighting conditions. It normally does that. And thank goodness, because otherwise we'd see bananas as having gone bad and turned all gray when we wandered in the dimly lit kitchen late at night. And without size constancy, we would think our friend was actually shrinking as she walked away, or we'd experience the doors stretching itself out on one side rather than opening towards us. So the big picture takeaway here is that all these weird illusions we've seen, they happen because the brain uses shortcuts, heuristics we might say, to interpret the proximal stimulus based on contextual information. All day long, our brain is working its ass off to construct these three-dimensional simulations of the world around us based on a bunch of ambiguous light waves projected onto our flat two-dimensional retina. It's actually pretty badass how accurate we normally are. And by the way, whether they put a name to it or not, artists take advantage of these sorts of perceptual effects all the time, as do architects, even going back thousands of years. Like the Parthenon pictured here, famous building, it's a bunch of identical parallel columns going straight up and down, right? Well, that's what they wanted people to see it as. That's what they wanted people to perceive. But since the human brain doesn't see things as they actually are, but constructs a guess based on predictable rules, they actually constructed the Parthenon's columns in a slightly weird way to create the illusion, the perception of identical straight columns. So they got people to perceive the top version. That's how people experience it when you're looking at the Parthenon from straight on, even though they actually built the building like the bottom here. They had to build it that way to get people to see it in the top way. Although in the bottom here, this is an exaggerated depiction of that. So in the real Parthenon, they made the columns bulge a little bit toward the middle to compensate for our brain's tendency to perceive parallel lines as curving inward. Also, the horizontal lines of the beams crossing at the top of the columns and the top step of the porch, those are bulged slightly. In reality, they built it this way, bulged slightly upward just to counteract our brain's tendency to perceive them as curving slightly downward. The columns lean slightly inward at the top to compensate for the brain's tendency to perceive them as spreading out as we gaze upward when you look up at the columns. Like, modern designers have to take into account human cognition if they want to be sure how actual humans will see their design. Okay, that'll actually wrap things up for this video of constancy effects and visual perception. In the next video, we're going to dive into actual theories of perception and see what the experimental evidence supports.